Okay, so welcome everybody. Today our speaker is Jincheng Yang, our member and postdoc here at the Institute for Advanced Study, and she's going to talk about new estimates for Navier-Stokes and the Inviscid limit problem. Please.
Thank you, Camila. I will just jump right into it. This is a joint work with Vincent from CUNY, Anna from Penn State, and Alexis from UT Austin. So the plan for today's talk is to cover a few topics. First, I will do a brief introduction on Navier-Stokes and some partial regularity related topics. Then I will present several new estimates, especially about vorticity and in general velocity gradient in the sense of trace. Then I will present several applications. The first is the so-called Inviscid limit problem, which studies the behavior of Navier-Stokes at very low viscosity. And then I discuss the Inviscid limit problem with a different set of boundary condition called noncharacteristic boundary condition. And if time permits, I will spend a few minutes on the idea of the proofs, but with high probability I will scroll that out. All right. So in this talk, we'll be dealing with, let's just focus on three-dimensional Navier-Stokes equation with incompressible condition. So the equation is the following. We have a momentum equation and we have divergence-free condition. So we have chosen the dimension units so that viscosity is 1 here. We will be working with two types of solutions. The first type of solution is called Lurie-Hoff-Wick solutions. And these solutions live in the energy space, which is infinity in time, L2 in space. And the derivative, one derivative in space is L2 in space and time. And these spaces are due to the fact that a priori we know for a smooth solution, there's energy conservation. And energy conservation says, if you look at the kinetic energy, which is the integral of u squared at some later time tau, plus energy dissipation between time 0 and tau, that is the amount of energy that is transferred to heat due to this heat dissipation term. So if you compute the summation of these two terms, it should be smaller than your initial energy budget, which is 1/2 L2 norm of the initial value. So here, let's for simplicity consider omega is just R3, and we have sufficient decay at infinity so that everything is well defined. So we know that for smooth solutions, energy should conserve, but because now we do not have enough regularity to show conservation of energy, there is a possible loss of energy due to lack of regularity. So here we have inequality instead of equality. So this type of solutions were constructed by Lurie and Hoff. They are global in time. And at that time, it's not unclear whether they are unique or not. It's still unclear till now, but we know for the first equation, there is no uniqueness in this class. Okay, so this class can be upgraded a little bit to the so-called suitable Wick solution, which can be obtained by the same argument, more or less. And this set of solutions has a stronger requirement on energy inequality, which is it not only satisfies this inequality, but satisfies this in a local sense, meaning that you satisfy this local inequality. The quantity on the left, this distribution will be a negative measure. If you integrate this measure on R3, you get, and from 0 to tau, you get the global energy inequality. And again, formally, this is obtained by taking dot product of the equation with u. If you are good with integration by part, then product rule, then you can see this yield this inequality with equality sign if the solution is smooth. Right. So now we know that both solutions have global existence in time, and they have finite energy in this energy spaces. But uniqueness is still in the air. All right. So let me go a little bit deeper on the issue of uniqueness. It has been established several uniqueness criteria, meaning that, okay, now the solutions live in this energy space, but if we know that they live in another space with better integrability, better regularity, then the solution has to be smooth. And these criteria are the ones which interpolate L3, L infinity L3 and L2 L infinity. So these are not locally reachable by our energy space. It's a little bit higher, but once you live inside those spaces, the solution is immediately unique and regular, and we know there are no other weak solutions. So on non-uniqueness, we know that mild solutions are non-unique. You can construct very wild solutions, but these solutions live in Holder spaces instead of this Lorentz spaces, energy spaces, I mean. And now we know that suitable solutions are non-unique in terms of the forced equation. So it's possible to construct a force such that with zero initial data, you can extract two different solutions. And this construction is inspired by instability construction for Euler solutions. All right, so I would like to use this picture a lot in my talk, which is to visualize where these energy criteria live here. And because we're talking with integrability in time and in space, so I use this diagram to illustrate the Lebesgue space LP, LQ, LP in time, LQ in space. So these spaces are represented by a dot in this third quadrant. So each point here corresponds a LP, LQ space. For instance, this dot will be L4 in time, L4 in space. So if you go to the right, you have higher integrability in time. And if you go upward, you have higher integrability in space. And so earlier we have energy space, which is this line, because we know solutions have uniform in time L2 in space integrability. It corresponds to infinity L2, which is this point. And we know that it's in L2 H1 dot, so it's L2 in 3D, L2 L6 by Sobolev embedding. And the space L2 L6 will be this point, L2 in time, L6 in space. And as you may have noticed, I use a particular way of numbering these indices so that I can interpolate with straight lines. So if a solution lives in this Lebesgue space and this Lebesgue space, then it automatically lives in every space in between. And of course, locally, it will live in every space beneath this threshold. So this is the threshold up to which we can construct weak solutions for any initial L2 data. And these spaces are the spaces with critical scaling. And the scaling for Navier-Stokes is a one parameter scaling. And it is the following. So essentially it says, let me jump to next slides real quick. So it means that, okay, if I have a solution on the left and I zoom in X, and also I zoom in T in the correct way, then if essentially I'm using a smaller ruler and using a faster clock, but if I make them to be the correct ratio, then the rescale solution is again a solution to the same equation with the same viscosity. And if there's just one parameter scaling to this equation. And if a norm that after rescaling is invariant, then this norm is called a critical norm. For instance, L infinity L3 is critical norm. After zooming in, the norm is remained the same. But the energy norm is worse than this one. It's called supercritical, because if you zoom in your solution, the energy gets larger. That's why, so these are spaces with critical scaling, and these are supercritical, and those are subcritical. So we have established actually the regularity criteria on the critical scaling spaces. So we know that once a solution reaches this level of integrability, it has to be smooth and it has to be unique. Unfortunately, the energy space is supercritical. Right. So other than regularity criteria on velocity itself, there is also regularity criteria on the derivative of velocity. So for derivative of velocity, we have these family of spaces due to Biot-Kato-Maeda and Vega. So if we can show gradient of U reaches this level of integrability, the solution also has to be smooth. Of course, you can establish maybe higher derivatives regularity, because there is always a 1/3 embedding using Sobolev embedding. So these are the finish lines, and we want to know how far we are from those finish lines. So let's do a quick review about current knowledge of a priori estimates for Navier-Stokes for Lorentz and suitable weak solutions. Lorentz solutions satisfy U in L infinity L2, gradient U in L2, L2. And the Sobolev embedding tells U is in L2, L6, and then you can interpolate. You can use various different methods to get other spaces for U, gradient U or higher derivatives. So here you notice that beneath L1, these are no longer Banach spaces, but you can still define quasi-norms. So these are the spaces where higher derivative live, and we also know that first derivative is in L infinity L1, and the second derivative is almost L2, L1. And you can go on for higher derivatives. So these family of results are obtained on the diagonal. So these are homogeneous in time and space for higher derivative as well. And then you can interpolate. But here I use dotted, well, dashed line or this empty circle, meaning that the solution is not LP-LQ, but a slightly weaker version. So today I will show that we can extend this picture to the lower half triangle, and showing that for higher derivative, we have these a priori estimates as well. Okay, but as you can see, this is criteria. This is the criteria for U to have full regularity, but we are a little bit away from it. And this is the criteria for gradient U, and we are also a little bit away from it. I don't think there is any immediate improvement that can reach the threshold, especially now we have all these non-uniqueness results. All right, so other than regularity criteria, there's another family called absolute regularity criteria, which instead of looking at higher integrability, we just look at the energy. For instance, this L2H1 energy, which is the gradient U in L2, which we know are finite, at least for suitable weak solutions. So this set of criteria says the following. Instead of showing that the solution is smooth everywhere, I want to show it locally. And to show it locally, I say, all right, I can separate the entire R3, 0T times R3, to two parts. One part is called the singular set, one part is for the regular set. The solution on regular set is locally bounded and locally smooth. The solution at the singular set is the, it's unbounded, of course. And so we call a point is a regular point if locally solution is bounded. And if this is true, then with previous criteria, we know we have regularity. And
excuse me, does it imply for all times? I mean, it's an inequality.
all time. So this is
Yes, I mean, it doesn't depend on time.
it does.
It calls for arbitrary time.
It does depend on time. So here, this is -1, it's in time. So B1 is a unit ball in space. So it's actually a space-time norm. Okay, so this theorem says the following. There is one way to tell apart singular point and regular point by looking at the energy of the rescaled solution, local energy. So if I pick a point, for instance, this point, and then I zoom in my solution using the canonical scaling. Remember, after zooming in is still a solution. I look at the solution in a unit cube, and I compute its energy dissipation. So I can zoom in and zoom in again, but if in this process, every time I zoom in, there's always some chance to see the energy above a certain threshold, then it has to be singular. On the other hand, for a regular point, if you zoom in and zoom in, eventually the energy dissipation of the rescale solution is approaching zero. There's a clear gap between the two cases. Using this local absolute regularity criteria, we can establish the partial regularity result, which states that the set of singular point is at most one-dimensional. And here we're talking about a parabolic Hausdorff dimension, but we can first think in terms of Hausdorff dimension. So a set is one-dimensional if I can cover them by boxes such that beneath any length scale, such that when I stack these boxes together, the total length is, say, bounded. Then it has finite one-dimensional Hausdorff measure. And the reason that the singular set is at most one dimension is we can do a quick proof for this. For every point that is a singular set, that's in the singular set, because it's a singular point, then every time I zoom in, I can have energy dissipation. The rescale solution centered at Tx has energy dissipation greater than the threshold, right? Which means if I rescale back to the original solution, the energy dissipation in a box of radius r is greater than small constant times r. So the energy dissipation is comparable to the size of the radius. Now we can do a covering argument. We cover all the singular points by boxes, pick a subcover, and then this disjoint subcover the disjoint subcover is after rescaling forms a covering of the singular set. And we can compute what's the total length because each length is comparable to the energy dissipation inside the box. The total length is comparable to smaller than the total energy dissipation in the summation of those boxes. And these boxes are disjoint, so the summation is a finite number. And that proves the singular point is at most 1D. And you can go a little bit further to show that the one-dimensional measure of singular set is 0, because these boxes are getting smaller and smaller. So this integral is actually going to 0. Right. So next I want to discuss how to extend the picture of integrability. And here I'm using vorticity because vorticity is related to velocity in a certain way, such that if you control vorticity, it's similar to controlling the velocity. Here, if you take the curl of the equation, you get an equation for the vorticity omega, which is the curl of u. It is also divergence-free, and it has a transport term, stretching term, and a dissipation. But here, although I'm taking out of the pressure, so everything is local in terms of u and omega. But if you think it as a system of omega only, the drift is generated again using a non-local way. It's the 3D Biot-Savart law. So, so the goal of the next section is to understand how big this vorticity is in the sense of trace. And I'm here talking the trace in a slightly general sense. I can take trace in space, I can take trace in time, and I can take trace in a submanifold, which is not necessarily a hypersurface. So vorticity is like one derivative of velocity. I want to measure the trace of higher derivative of vorticity, which will be similar to n+1 derivative of velocity. Apart from the mathematical interest, this estimation also comes from the physical fact that in a lot of physical phenomena we saw, a lot of vorticity is concentrated on a submanifold with a lower dimension. For instance, we have this picture of vortex ring, vortex streets, as well as tornado, where you have a lot of vorticity on a column, and away from this column, the vorticity is relatively small. So the estimate we have is one uniform estimate for all the higher derivative, and the statement is the following. There's a way to bound any higher derivative of vorticity using the help of one auxiliary function, which I call the scale function S. The scale function assigns every spacetime point a number, a positive number, such that the vorticities and derivative is bounded by the scale to some minus power up to a constant. And well, we know that
Sorry, does S depend on N?
S does not depend on N. So it's just one function that depends on the solution, but does not depend on the number of derivatives. So there might be a constant in front of this, which depends on N. So this function tells me at each point what is the correct scale to look at it, such that all the higher derivatives can be bounded. And the next task is to, okay, I control it by the scale function. So I want to understand how big the scale function is. Right here, I'm taking the scale function in spacetime. Now it is a function of 3, but if I only look at its trace on RD, then it is bounded in the weak norm LD+1 in spacetime by energy dissipation up to a constant, up to a remainder which depends on distance from the initial time. So if I have a hypersurface or just an open set, then I can take tracing time. That is, I can fix a t such that at that t, the function can be taken trace and estimated in L d minus 1 week, again, using the energy dissipation. Okay, so here RD can be replaced by Lipschitz graph of dimension D. So how does this theorem come from the scaling argument? Well, we know that the idea is that there's a battling force between the transport term and dissipation term. At a very small scale, dissipation is stronger, so the equation behaves more or less like a heat equation. So our task is to find, if I keep zooming in, then after a certain scale, the solution is very smooth, and then we stop at the scale, and then we can estimate derivative using that scale. So to put the idea in one sentence, that is, we find a way to quantify at which scale energy is dissipated. So at every point, there is a different scale, and the scale depends on how much business is going on near that point. So for instance, here I have a picture of a flow passing a solid body. Then in this region where there are nothing much going on, the scale is relatively larger. And here, when there's a lot of gas, then the scale has to be smaller. And the way to find this scale is just keep zooming in until you see the rescaled energy is beneath that threshold. So to do that, first we need one scale epsilon regularity theorem, which is a corollary of my earlier work with Alexis. So if we just look at the unit cube, then with the additional assumption that you have zero average, then the average energy dissipation is beneath certain threshold, guarantee L infinity bound on any level, any number of derivative on the vorticity by some number which depends only on the number of derivatives you take. So the argument is that I can just, first find a scale such that after scaling, this is smaller equal than epsilon 1. Actually, to find the best scale, we zoom in until these two are exactly equal to each other, and then we stop. After stopping, we know that the rescale function, rescale vorticity is bounded by some number. So we scale back, and then we can control all the derivative in terms of the scale function. Right?
Sorry, what does it mean, zero assumption?
Right, because your U doesn't have a zero mean, right?
Yes, so here I'm using, so here the theorem asks that U has zero mean. But here I'm cheating a little bit because I shouldn't just use the unit cubes. I'm actually using a curved cube. So I'm following the flow, taking out mean velocity, such that after a change of coordinates, using the Galilean invariance, it becomes a solution in the unit cube, and that has a zero mean. So the entire argument is not only not built on this regular cylinders, but really this curved cylinders. And for these curved cylinders, we do have a maximum. We do have a covering lemma, so that we can run the usual.
Simple question.
Yes.
Velocity contains potential part, which is gradient or something, and rotational part. And
Yes.
here you compare total velocity with purely rotational part.
Exactly.
Where goes the potential part?
So the trick is that in the beginning, if you just take the curl of the equation, the potential goes away.
No, it doesn't go away because U involves it.
Yes, well, we need some estimate on the size of U.
Curl inverse is
Yeah.
defined after potential part.
Exactly, but here we control U. the energy of U, not only just vorticity. Here we
And
control.
that involves potential part.
Yes, yes. So we also know that, well, if you think U as potential, we also know that the potential is smaller than some threshold. Yeah. So we are, yeah, we do know that every term in the equation is small, right? We know U is small because it has zero mean, and we also know its derivative is small. So everything is small to begin with. All right, so well, after this, all it's left to do is control the scale function and taking a trace of the scale function. And this part can be done rather in a very technical way. It's really irrelevant to the equation at all. It's really just a harmonic analysis exercise, I should say. That if you can define a scale function by just doing rescaling of some function until it stops, then you can show this scale function is in LP, LQ, and you can take trace with the correct choice of P and Q. So this is what we have. That's why you see that all these lines are, well, more or less parallel to each other, because they are really just bounded by the same function to different negative power. And using this method, not only I can extend the picture to the lower right triangle, I can actually reprove previous results and understand all these previous a priori estimate using different methods in a uniform way. By the price that now the estimate is slightly weaker, but the scaling is the same. So that I like this because it tells us that the higher derivative estimate can sometimes be traced back just to estimating the size of the scale. And this, I think, for any system with scaling symmetry and absolute regularity, you should be able to do this. All right, so for the remaining of the talk, I want to present application in the Inviscid limit problem using similar ideas on the estimate. So here we're dealing with Navier-Stokes with viscosity that is very small. If there is no viscosity at all, that will be Euler equation formally. And on the left, we have an ideal fluid, which is incompressible and inviscid. So this is a picture of a laminar flow passing an airfoil. As you can see, as the flow passes this airfoil, the streamlines are more or less parallel to the boundary. On the right, you have an experiment of a wind tunnel where you see real air moving past an airfoil. But even though air has very, very small viscosity, the behavior between the two solutions are still very different, especially in this part. All right, at the bottom half, they're more or less the same. So this is also laminar and solution stays more or less parallel to the boundary. But on this downwind direction, there's a region where you see a lot of chaotic and turbulent behavior. So this is one thing we want to do, that is to compare how different these two solutions can be as viscosity goes to zero. Another thing I want to do is to understand the rate of energy transfer, that is, how much energy is transferred from kinetic to heat. We know that for the inviscid fluid, there is no friction, so it generates zero energy. But on the right, there is a lot of turbulence, so it could generate heat. So I want to also understand what is the limiting behavior of the amount of heat that is generated. Other topics we can discuss on the Inviscid limit include, let's say, is it true that beneath certain beneath certain viscosity threshold, the solution becomes turbulent, and is the solution unique and stable, and does the turbulent solution dissipate energy? And if I take the limit, what is the limiting energy that is dissipated? What is the limiting amount of energy that is lost due to lack of regularity, so on and so forth. And well, if I take a sequence of Navier-Stokes solution, I take its weak limit, does the weak limit conserve energy? Right. These are all questions related to low viscosity Navier-Stokes. Okay, so to put it in mathematical terms, here I'm going to do is I'm going to imagine there is already an example of an ideal fluid. For instance, I fix an Euler solution that is regular, for instance, C1, such that it's actually a classical solution to the Euler equation on the left. So on the right, we have a family of Navier-Stokes equation indexed by viscosity nu, which is a positive number. And here I allow them to have slightly different configuration. I allow slightly different body force, different initial data. They are both divergence free, of course. And there is a difference of the boundary condition as well. So for now, I'm assuming we're in a bounded and smooth domain, and Euler solution is impermeable, such that this velocity on the boundary is only tangential to the boundary.
Is your force assumed to be Gaussian or something, white noise, or just some external force?
So for here, it's an external body force, which is regular. So here, you can think, say, I think a continuous force is sufficient here.
Okay.
And for Navier-Stokes, this can be a little bit more rough. This is allowed to be rougher. Yeah, because I want to consider weak solution to Navier-Stokes as well. All right, so the physical dimension we take is dimension 2 and 3. Unknowns are velocity and pressure, but the pressure can be obtained by doing a projection of these terms, so it's less important. Viscosity constant here, it's just a sequence of number, right? And formally this corresponds to the case where viscosity is 0. So the goal is to study the limiting behavior of Navier-Stokes as the configuration converges to the configuration of Euler. And here I'm taking nu to 0, of course. And here the body force converges to the body force of Euler in L1, L2 space. And the initial data converges in L2 space. And these spaces are the ones in which we can construct Lurie-Hopf-weak solutions. So given this data, there is at least one solution to Navier-Stokes on the right. We can simplify a little bit and just think in our head a simple plug flow. Say Euler can be just a constant flow. And Navier-Stokes starts a little bit different from this one and with a little bit of body force. So the goal is to understand, well, does Navier-Stokes solution converge to Euler solution? And one way to analyze this is using the boundary layer theory that is developed by Prandtl, who take the difference and denote the remainder to be boundary layer. And the name comes from his asymptotic analysis, in which he finds that this part is majorly supported in a thin layer near the boundary. And this layer has a width of order square root of nu. And this is obtained up to some condition, which is a variable gradient, pressure gradient condition. It means that, okay, if there's no flow separation, if the flow is more or less just parallel near the boundary of your interest, then you can think Navier-Stokes solution as the summation of an Euler solution that is inviscid and a small correction that is more or less supported near the boundary. But this assumption is not always satisfied, as we can see from the previous picture. So here is a picture to illustrate when this theory works. So here we have a laminar flow passing a metal plate. And in the beginning, it's more or less like a constant vector. And when it passes through this metal plate, away from the plate, it's still kind of like a constant. But near the plate, there is a drastic change in velocity. It drops drastically from order 1 to order 0 to match the boundary condition. And this width is of order square root of nu. Okay, so but I want to understand if we can incorporate the case with turbulence. So we're going to just look at the weak solutions without using assumption on pressure gradient. So this is an open question even in dimension 2. We don't know if unconditionally solution to Navier-Stokes converge to Euler. There are conditional results. The most famous one, I should say, is due to Kato, which says that if together with those convergence, we know a third convergence. And this condition analyze the amount of heat generated in a thin layer near the boundary. And this is a different layer from the Panto layer. This layer has width of order nu. So if you compute the amount of kinetic energy transferred to heat in a very thin layer, and if this converges to 0, then we have convergence from Navier-Stokes to Euler, uniform in time, L2 in space.
Yes. Assume also the U Euler is smooth.
Yes, of course, yeah. So throughout the remaining of the talk, I'm going to assume we know that there's a good configuration, a good smooth Euler solution.
The Kato condition is not unconditional. It's conditional on the limiting solution being smooth, existing, and you start with initial data that are compatible.
Yes, yes. So the external force needs to be very close to some smooth force, and initial data needs to be very smooth, close to some smooth initial configuration. Yes, that's true. All right, but the problem is even under those constraints, whether this can be dropped, it's still open. We don't know if this is unconditionally true. So there are other types of conditional result, and there are unconditional results with assumptions on say, symmetry or analyticity, or in slightly different configurations. For instance, you can assume that dissipation is different at different rate in different direction, which happens, for instance, in atmosphere. But the original problem is still open, and I can show you where the difficulty comes from. So here it's simple energy estimation. So you take the difference of Euler and Navier-Stokes, you take its L2 norm squared, and then take time derivative. The goal is to show that this converges to 0. So let's see how it evolves in time. We find that this satisfies one inequality of this form. In this inequality, there are a few terms that are less important. One is this term because Euler is assumed to be a smooth solution, so this is some fixed number multiplying nu, so this will go away at the rate of nu. This term can be normalized because we're assuming Euler is smooth. So for instance, it's Lipschitz constant in x, we can assume it's L1 in space, L1 in time. We can add all the assumptions we want. So the main player are these three terms. The red one is the one we want to control, the size of boundary layer separation, the difference between Euler and Navier-Stokes. The orange one is another thing I want to control. As stated in the beginning, I want to understand how much energy is dissipated through heat. And the blue one is the work done by the boundary friction to the Euler solution. Because here tau is the stress tensor, which has two components. One is the pressure, one is the friction on the boundary. But the pressure is always orthogonal to the boundary. Velocity is tangential to the boundary. So the pressure doesn't contribute to this term. So the power of boundary stress is entirely due to friction. So if I can control this, how much friction does the work, I can control how big this is. If I can show this converge to zero, then this converge to zero as well. So that's the game. And okay, so here is a picture to show where those players live. So this is a big difference between Navier-Stokes and Euler. That's the so-called layer separation solution. Gets away from the solution, from the boundary. And here, for instance, there's a lot of chaotic behavior and velocity gradient becomes very large. So there's a potential, well, possible energy dissipation over there. And here I say boundary friction is doing a lot of work because the velocity drops from Euler 1 to Euler 0 at a very short distance, meaning velocity gradient is very large. And when velocity gradient is large, heat can be generated. Right, so instead of proving inviscid limit, which I cannot do, I want to understand the problem from a different angle. That is, I just want to give an upper bound on how big these quantities are. So here I'm again fix a regular Euler solution and a regular Euler force, regular Euler initial data. I take any possible sequence of Navier-Stokes solution to those approximated system such that they converge to the Euler configuration in the energy spaces, in the correct spaces. And I ask myself, what is the largest possible difference between Euler and Navier-Stokes? What is the largest amount of energy dissipation in the limit? And what is the largest possible work done by the friction? And the result is the following. All three terms can be controlled by an upper bound of order a cube t times s, where a is the boundary velocity, t is time, s is the surface area, up to some exponential factor, which depends only on the Euler solution. So this is under the assumption that solution of Euler is smooth. And one interesting thing is that this constant C is universal and is independent of everything. It really comes from, say, Sobolev embedding and other dimensional dependent constants. All right, so let me jump a little bit to show you more or less what the proof needs. So earlier we showed that, okay, this blue term can control the red and the yellow term. So the main goal is to control how big this blue term is. And the blue term is a pairing between normal derivative of vorticity of velocity and Euler, which is a smooth vector field. So the goal is to control, the goal is to control because this equals to nu times omega nu. So the goal is to control the size of vorticity on the boundary. So we need a trace estimate of the vorticity. And we want a trace estimate that is uniform in terms of the Inviscid scaling. So this is slightly different from my previous trace estimate because the previous estimate is only in interior trace and it gets worse and worse as you get closer to the boundary. So I need a boundary trace analog of the previous result. And because it's a parabolic equation, there is enough regularity to take trace. But if you just do the linear trace estimate, the scaling is bad when you take the Inviscid limit. The correct number you get is L4/3 if you use linear trace, and this bound gets worse and worse as the viscosity tends to 0. So we need to invent a new trace estimate, which is it's uniformly bounded by something that doesn't go away in the Inviscid limit. So okay, due to time constraint, let me just say that this is a weaker version of the previous interior trace estimate. But although it's super weak, it's sufficient for us because we just need to understand how big it is or pair it with a smooth vector field. And by controlling this by this upper bound, which is comparable to the energy dissipation, we can do a simple Young's inequality and kill these terms, absorb it to the left, and bound everything by a cube TS. So that would be the main idea. All right, so then we actually also recover the result of Kato. If in addition you assume Kato's condition is true, we have now a new proof for Kato's criteria. Okay. And we generalize it to non-characteristic boundary condition case. So instead of setting 0 velocity on the boundary, we prescribe it to be some smooth vector field. And after this change, we get more or less the same upper bound, but we also get a lower bound on energy dissipation, which is comparable to the upper bound. So I'll just present this result and conclude my talk here. So we have upper bound and lower bound of the same order on the amount of energy dissipation, meaning Kato will fail when you have inflow, outflow boundary conditions. All right, thank you. Yes.
There is a well-known tabular vortex solution by Burgers, and somebody was discovered that even before. So that solution has a normal dissipation.
Yes.
Demonstration, it has width of the order of radius of square root of nu, but then when you integrate, it cancels nu in front of integral of radian square. So if you take one such solution and another far away, it will also be a solution of Navier-Stokes. You could have a lattice of these vortices parallel, right? And that will be an example of the anomalous dissipation. So could that be used in inequality? I mean,
Yeah.
that's an example, but maybe there is some way of using that example to have a very precise definition of inequality.
Yeah, I would like to know how quantitative these examples are because right now, even though we have upper bound, we don't have an example showing the upper bound is sharp.
Well, this is a well-known exact solution of Navier-Stokes, and if you take Newton's integral gradient square, it is fine in the limit of nu going to 0.
Yeah, we can talk
Yeah,
about
yeah.
this later. Yes.
You can estimate the time derivative too in your first theorem, right? Or am I wrong?
Because when we take out the mean velocity,
Because you're taking out the
you are
mean
changing the solution a little bit. So
Uh-huh.
there might be a parasitic solution.
But I was
From
saying
pressure.
because so can you actually control the pressure?
No,
Okay,
I don't.
so you cannot use the equation to kind of try to control the dtu by writing everything on the other side.
Yeah, so the reason is that if we look at the equation, just look at the equation itself. Okay, so this term and this term are orthogonal. So if we can control Laplace u and u dot gradient u, then we're done, right?
So
But the problem of u dot gradient u is that u is controlled in slightly worse spaces.
yeah, so your result is local, so it might actually have inside, say, a function of time times the harmonic function. That's what you're saying.
Yeah. Yeah.
Because your S of Tx is just defined, even for a local solution.
Yes.
Okay, and in your proof, this would be a manifestation of the fact that you're subtracting.
Yes, I'm
The average?
subtracting the average velocity.
Yeah. So actually, on that example, you would be traveling with the flow.
Yes. That's why I chose to dance with vorticity rather than other symmetric part of velocity gradient. Because looking at the vorticity equation, I can throw away the pressure.
So do you have criteria also for the higher derivative? I mean, because you have this triangle, this where you are and what you want, right? And you're always below, but I'm wondering when you do with higher derivative, does it get nicer or something?
Well, for instance, for second derivative, of course, you get a similar criteria using solver embedding. I'm not sure.
I think the distance is probably always the same.
Yeah, I was just wondering whether there
No, I don't think it gets. I don't think you get closer, right? I mean, for higher derivatives, somehow, I guess the kind of like,
were the same amount.
right, I mean, the kind of nice triangle is it will simply sort of parallel translate, I guess,
It's definitely not better.
right? I mean, it's definitely
Sure.
not going to be better, but I don't think it's even going to be worse either, right? I mean, because in terms of scaling, it should be.
Right, so Camilo, return to your previous question, I think there is a potential fix. So here we're estimating vorticity. And this is a local estimate, so which it works for any solution in a bounded domain. But if you're considering solution in R3 or in a torus, we can make use of the pressure as well. Then we have, so this picture is legitimate for torus or in R3. So in those cases, we can make use of the pressure to do something. Because we can show second derivative pressure is L1 in time space.
Okay.
Yeah, using that,
Then you would be able to estimate the time derivative as well, I guess.
I think so, yeah, then you don't still need to travel a little bit with the solution, but
Well, if
now
you-
you have additional knowledge on pressure, maybe you can.
Well, if you have the additional knowledge of the pressure, you can simply write, dtu, and then everything on the other side doesn't have a time derivative. The only thing which is appearing is the gradient of the pressure compared to what you estimate.
Yeah, but here we can only use second derivative of the pressure, which has the correct scaling. So it is still possible that it has a large first derivative of the pressure. So
Okay,
I should remain
okay.
suspicious.
Yeah, well, that would be really interesting. The time derivative times the space derivative. So maybe that is okay.
Yes.
But anyway, maybe we discuss this.
Yeah, for these solutions,
Somewhere else.
the time derivatives are obtainable.
Okay, so
Just one, maybe last one question. So with the gradient, you just use Sobolev to push a bit higher the previous line, right? The U line. That's how you get the 2,6 cross. So if I do the same for the action, I guess this doesn't work, right? If formally I use some Sobolev embedding, it doesn't push me a bit further that line. Right?
Yeah,
It's not force for the gradient.
So I mean that because you know that this is the finish line for gradient U. There will be a similar line for second derivative U. Because if you know second derivatives are here, the first derivatives are here. Right?
Yeah, but that's not the optimized line. I was just saying that what you know by just embedding from the circle on gradient U, you pushed the U in L26 just by Sobolev embedding, right? That it's
Yes, yes.
you went a bit away from the axis. You see,
Yes.
that line is the only one which is not symmetric with respect to the diagonal. wondering-
Yeah, so this one is the only one that looks different from the others.
Okay, the other one you're not able to push
Yeah.
to make them a bit symmetric.
So I think here is exactly 1/3,
Okay.
but
so-
here is a little bit larger.
Okay.
So here we lose a little bit somehow.
Okay, there are no more questions. Thanks.